I hope everyone is doing well during these challenging and uncertain times. My name is Priyanka Yadav and I will be your moderator today. I, along with the YES webinar organizing team, are excited to be hosting this session today. Today's webinar is on viewing climate signals through an AI lens. Now, before I introduce our speaker, I would like to cover a few housekeeping topics. Please be polite and respectful to the speaker and all participants. Please keep muted and close your video during the presentation. If you have a question for our speaker, you can type your questions in the chat box first, or you can also use the raise hand option. We'll unmute you during the question answer session and you can ask your question. But please be mindful that other attendees may also have questions for the speaker. We record all contents in presentation, Q&A, and messages in the chat box. We'll share a link with you after the event is complete. Now, coming to the part for which you all are here today. I'm pleased to introduce today's speaker, Dr. Elizabeth Barnes. Dr. Barnes is an associate professor of atmospheric science at Colorado State University. She obtained her bachelor's degree from University of Minnesota with double major in mathematics and physics, and received her PhD in atmospheric science from the University of Washington in 2012. Dr. Barnes' work covers a variety of topics such as large-scale atmospheric variability and predicting its behavior over a range of timescales and climates, health-related climate impacts, and data science method for climate research. She is involved in a number of research community activities and has received numerous awards. Because this webinar series is focused on early career researchers, just to inspire you all, in 2014, she was the recipient of an AGU James R. Halton Junior Scientist Award, and in 2020, she received the AMS Clarence Leroy Meisinger Award. It is an extremely prestigious award for an early career scientist. And if I go in detail, I can take the next 30 minutes just to cover her introduction. So without further ado, I would like to welcome Dr. Elizabeth Barnes. Dr. Barnes, over to you.
Thank you, and you can hear me and everything, yes? Good. Yeah. Okay, so thank you everybody for having me. So let's make sure, okay, good, make sure my slides work. So today I want to talk to you about this big topic of viewing climate signals through an AI lens. And first of all, before I go into any of the actual science, I want to acknowledge the fact that this is not work that I have done by myself by any means, but in fact is a large collaboration. And a large part of that collaboration is with early career scientists, especially the parts about that we're doing next and moving forward. So this includes master's students, a PhD student, postdocs, but then also some faculty across a range of topics. I know this particular webinar series is not just for atmospheric scientists, and part of my point of this talk is hopefully to teach you something interesting about climate science, but to give you tools that are much broader and more applicable to all earth sciences. And as you can see, my collaborators include computer scientists, data scientists, as well as a climate scientist. So this is really a group of people trying to think across disciplines and boundaries. Okay, so machine learning for geoscience. I'm not sure of the background of this group in terms of machine learning techniques, so I decided to assume you know nothing, and we're going to build from there. If you do know something, hopefully, by the end of this, I do believe you'll still have learned something new. So many geoscientists or earth scientists think about machine learning this way, and I certainly did. Your data goes into some black box, and then out pops a prediction, and you have no idea what happened in between. And there's a comic that I really like where this person says, so this is your machine learning system. And the person on top of the pile says, yep, pour the data into this big pile of linear algebra and collect the answers on the other side. The person says, but what if the answers are wrong? And the person says, well, just stir the pile until they start to look right. And this is sort of our feeling of machine learning, is you just stir a little bit and numbers pop out that may or may not be correct. And what I hope to convince you of today is that they really are not black boxes. You've probably heard that phrase many times, but that was maybe 10, 15 years ago. People thought of these as black boxes, but these days the computer science community have really started putting out products and tools that are game changers for machine learning methods for science. And so that's one of my big goals today, is again, I hope to teach you something about climate change and climate science, but if you get nothing out of this talk, I hope it is that there are visualization tools out there to open these black boxes and look inside at what's happening. So machine learning for geoscience is not new. In the private sector, many of you have probably seen applications of finding a cat or a dog in an image. Computer scientists seem to love cats. And this type of object classification has been used to find extreme weather patterns from Earth science data. Super resolution and fusion can lead to downscaling and blending. And video prediction in the private sector has been used for short-term weather forecasting. On top of that, in my specific community of climate science, these methods are also being used right now to try and model clouds in climate models, something we are not very good at. And they're making a lot of progress in this area. And finally, a recent paper, for example, that just came out on weather prediction actually attempts to replace a weather prediction model with a purely machine learning model and shows that it doesn't do all that bad, which is pretty awesome and surprising. And this is a paper that was just submitted. The point being that they spent, a few months on the project, and if we were to spend more time on it, could we actually start replacing weather models with machine learning methods? Okay, I give you all of these examples in the atmospheric science community, at least, because I'm not going to talk about any of those examples. That's not what I do. I'm going to instead talk about extracting a signal from noise, which is really what many of us as Earth scientists do. So the atmosphere itself is noisy across many timescales, and separating the signal from the noise is never easy. So whether noise can interfere with understanding how teleconnections or how one part of the globe talks to another part of the globe on weekly timescales, and then on yearly to multi-decadal timescales, the slow up and down of the climate system can get in the way of identifying the human influence on climate or identifying anthropogenic climate change. So really, the methods I want to talk to you about today are really about trying to extract the signal from this noisy place we live in. Now, we have lots of tools. Many of you as Earth scientists use things like linear regression. Linear regression is great, and I in no way want to replace the tools you already use. For example, linear regression is good for just looking at changes in temperature over time. Fourier analysis or spectral decomposition is useful for understanding the wiggles of different time series. And finally, we use something called principal component analysis or empirical orthogonal function analysis, depending on if you've heard either of those phrases, to look for patterns of the climate system. These are all great tools and great methods that stand the test of time. I just want to suggest that machine learning techniques offer an additional set of tools. They're not supposed to replace what you already do, but maybe they're a new tool for your toolbox. And I hope, and that's how I want to present them today. Okay, so let's get to the science question. What is it I'm actually going to do? So climate change in the 21st century can really be thought of as a signal to noise problem in terms of identifying it. So here's a plot many of you have probably seen something like this, where we're looking at the change in temperature from the end of the 21st century, so 2070 to 2099, minus the beginning of the 20th century from climate model output. So, and this is using a future climate scenario called RCP 8.5, if you're familiar with these. So the first thing to know is this is an average over 29 different climate models. When we look at it, the first thing we see, if you just take a second, look at this plot, what is it that jumps out the most? It's that everything is red. Okay, what does the red mean? It means that the globe is getting warmer in these simulations. It's climate change or anthropogenic climate change. We know this. Okay, good. The next thing you see is probably that the North Pole or the Arctic is redder than the rest of the globe. This is known as Arctic amplification, or the fact that the Arctic response to climate change is amplified compared to other locations on the globe. And this is well known, and we're gonna come back to this near the end of the talk. Now, when you look at this plot, I have hidden all the uncertainties and error bars. They don't show up anywhere. You can't see them, but they're there. And so I want to talk to you about what they are. So there's really two sources of uncertainty in this plot that I'm not showing you that I want to talk about. The first is known as structural model uncertainty, which I find to be a very large phrase, when really what it means is we don't know which models are right and which are wrong, but all of our models are different. So this is this uncertainty in the fact that different climate models can disagree with each other on the response to climate warming. And the second one is the fact that there's something called internal variability or climate noise. The fact that any one year is never going to look like any other year just because the climate's going up and down, even without climate change. Right? The weather today and the weather tomorrow are different. So that's been averaged out because I've averaged over two 30-year time periods over 29 different climate models. So all of that has averaged out this internal climate variability to give this really pretty plot. Now, why is this an issue? Well, here's the real world. Here's observed present day trends over the past few decades. Okay, so the question is, how can we tell which changes are the signal, which ones are due to anthropogenic climate change, and which ones are the noise when we only have one observed Earth and we can't average over many Earths, wouldn't that be nice, to try to extract the force signal from the noise? So the big question is, with climate models, we can average them together, but with the Earth, there's only one of them. And we don't know which climate models are right. So the question is, how can we look at the observations and point a finger and say that's climate change or that's not? So that's the question we're going to be attacking today. All right, so let's talk about methods. How are we going to approach this problem? So neural networks 101. If you're familiar at all with a neural network, they have often been used, as I said, for computer scientists in identifying images like a cat and a dog. So you input an image of a dog, it goes through this network. This is really cool little movie, and out pops the prediction dog, right? Okay, cool. But in the example I'm going to show you today, I'm not going to actually really care about the prediction. Actually, the prediction I'm going to make is so easy that you certainly don't need a neural network to do it. All of you are going to be able to know the answer. That's not going to be the interesting part. The interesting part is after my neural network makes a prediction, a boring prediction, I'm then going to look inside and ask, how did the network know that was the right answer? What did it learn to make that prediction? And that's where the science is going to come in. And that's where I think these tools can be really applicable across Earth science. The Earth scientists, because as scientists, the question we often want to know is why or how, not just make a prediction. And that is what these visualization tools allow us now to do. So what's a neural network? You've probably heard deep learning thrown around in the news, at least. And I want to show you that they're not that complicated, really. So here's how it works. This is the building blocks of a basic neural network. You have some input, x1 and x2. These are my yellow circles. And they are connected to a blue circle called a hidden unit, if we're going to use the fancy vocabulary here. And each of those connections is associated with a weight, a W1 and a W2. Now, if you take the x1 and multiply it by W1 and take the x2 and multiply it by W2 and sum it, there's my summation inside the blue circle, and add a y-intercept, or what computer scientists call a bias term, you get what you have at the bottom, which is W1x1 plus W2x2 plus B. That's what's happening at that point in the network. So far, all I've done is linear regression, right? Pretty boring. We can do this. This next step is where the neural network actually becomes nonlinear. So it becomes different than multilinear regression. That is, we take this value and we push it through an activation function or a nonlinear function that makes it interesting, takes it from the linear place to the nonlinear place. And otherwise, that's it. The training of the network is merely determining the W's and the B's. So this looks easy, right? This is what everybody's excited about. But now I'm going to put all these together. So the output of one of those blue circles, one of those blue units, becomes the input to another blue unit. And there's a weight associated with that connection. And then I'm going to add all of those together, add a bias term, push it through a nonlinear function, and then that's going to pop out the other side and go into another and another. And as you can imagine, very quickly, these can become very nonlinear and complex. And just a fun point of fact, if you want to talk about deep learning, you just need 2 columns of these blue units, and now you're doing deep learning, which is pretty, it makes you realize, oh, that's it? I thought it was something magical happening. And the answer is not really. So the whole point of training a network is searching iteratively for the W's and the B's that make your fit the best. And here's an example of using a neural network to fit a line. All right, and it iteratively is looking for that best slope and that best y-intercept until it finds it. The same idea when we have much more complex networks. Okay, so that's our 101. Enough lectures for today. What are we going to do with this? Well, here's what we're going to do. We are going to train a neural network to predict the year of a map. So let me tell you what I mean. I'm going to take a map of, say, surface temperature of the year you were born. So think of that year. That year has some map of annual mean surface temperature. So you can picture some map in your head of the year you were born. I'm going to take that map, I'm going to put it into my network. It's going to go through the hidden layers, and then it's going to output one prediction, and it's going to output its guess of what year it is. So think of the year you were born, that's the right answer. And we want to train a neural network to figure out how it can look at a map and guess what year it is. So we are going to use a relatively simple network with only 2 hidden layers. And these can become far more complex, but we didn't need it to be complicated in order to succeed. So why make it more complicated than it needs to be? Okay, so hopefully, since I can't see your faces, my hope is that this makes some sense. We're going to put in a map, and we want the network to predict what year it's from. So let's try an example of something I know is going to fail. I like to always start off by failing miserably, okay? So what I'm going to do is I'm going to take data from a control simulation of a climate model. That is, in this simulation, there is no anthropogenic climate change. It's just the same forcing every year. And the only thing making the weather and the climate different from year to year is just internal climate variability, the ups and downs of the pressures and the weather. Because of that, every map could be from any year because there's nothing special about the year. So let's see how the network does. I'm going to show you a lot of these plots. So I'm going to orient you here. The actual year, the true year of the map is on the x-axis, and the year predicted by my neural network is on the y. Now, the gray dots show the training data, the data I use to determine the W's and B's in my network. And they look amazing because that diagonal line is the one-to-one line. That's a perfect prediction. But the black dots are data it's never seen before. And it shows you that this network is terrible. It hasn't learned anything real. This is an example if you're familiar with the phrase overfitting. I have overfit to the gray dots, and the black dots, the data it's never seen before, fail miserably. And so because the variations in this simulation are only due to internal climate variability, there's really nothing for the network to learn that helps it identify one year versus the other. That is, there are no reliable indicators of the year. So with that said now, what is my network actually doing? My network has to try and learn regional signals that are reliable indicators of the year. Put another way, it has to learn regional signals that are indicative of a certain amount of CO2, for example, in our atmosphere, of some sort of climate change signal that tells it, it's not 1921, it's 2021. Okay, so let's see how it does. Now, the answer, of course, is it does okay, or I probably wouldn't be giving this talk in the first place. So, same plot as you've seen before. The actual year is on the x-axis, and on the y-axis is the predicted year. And this is when I'm training and testing over many, many different climate models. Some of the climate models were used for training. They are the gray dots, which you can barely see because they're hiding under the colored dots. The colored dots are the models that the network was not trained on. So it's data it never saw before, and here's its prediction. Now, first you can see that, especially after about the 60s or 70s, the network becomes pretty good. Those dots fall along the one-to-one line, saying that given a map, the network knew what year it was from. which is pretty cool. Second funny story here is my computer scientist colleague was helping me code up this data originally. And after a few weeks, we had a meeting and he said, Libby, I've tried so hard, but there's something happening between about 1920 and 1960. I cannot get the model to train over that period. And here's an example of him thinking it had something to do with the way he'd set up the neural network. But as a scientist, I look at that and I said, well, that's because the signal's so weak. The neural network can't possibly find any indicator of climate change yet. It isn't until about the 60s or 70s that it finally starts finding patterns that are reliable indicators of climate change. So in that sense, the fact that it's flat at first makes complete sense and tells us that we might actually understand what's going on. And that's an example of the fact that I think that as earth scientists and as geoscientists, it's very important that we are a part of bringing machine learning into our community, because we understand our data and we understand the physics. And so when we look at this plot, we see science rather than a model failing to train. Okay, so this is neat. This is, I'm very excited. I love this stuff. Okay, but here's one other thing that's pretty cool. Is remember how we only have one Earth, only one set of observations. So we can't train on one Earth because we need more data than that. But we do have maps of surface temperature that were observed every year. For example, each of your birthdays, as I said. So now that we have this trained network, we can just feed it maps of observed surface temperature and see what year it thinks it is. If our climate models are totally wrong and biased, it's going to do a horrible job on the observations, right? Because this neural network could only learn what it learned from the climate models. So the question is, how does it do? And those are in the white dots, is now the observation. So this is the predicted year of the, based on the neural network's prediction of observed surface temperature. Now, I don't know, again, I can't see your faces, but you should be very impressed. I was very impressed. And the reason I was impressed is we all know that climate models, they're wonderful tools, but they're never perfectly right. And yet somehow this neural network using this climate model data was able to identify the reliable regions that are also observed, which is pretty cool. Another cool game we can play is, remember how I had that long control simulation with no anthropogenic climate change in it? We can put maps from that simulation through our network and say, what year do you think it is? And when you do that, the network never thinks it's a year later than 1940. And that's because there's no climate change in those simulations in the first place. So that's a fun test. Okay, so, and you really see that these two depart in the 50s and 60s, suggesting, again, this is when the signal really appears. All right, so if you've been following thus far, you might stop and say, wait a second, this is temperature. Temperature is one of the most robust responses of climate change. If I take a global mean of temperature, everybody see those hockey stick type plots before? The ones that just shoot up? That's a pretty clear signal. Maybe the neural network is just taking a global mean temperature and saying, hey, it's hotter this year than the other year, so it must be a later year. While true, that would be pretty boring, to be honest, because we didn't need a fancy neural network to do that. So what we do next is to test whether the neural network is just using the global average, is we're going to remove the global mean from every map. That is, the neural network can only use information about comparing one region to the other, because every map's global mean is 0. And when we do that, we get this result. Now, first of all, the result is certainly not as good as the left-hand side, because we've removed a very important piece of information. However, it's not terrible either. It actually still does generally get at least the right decade, give or take. So a few things to note. First of all, you'll note that the observations have shifted up. That suggests that when I remove the global mean in this way, the observations appear to be 20 years ahead of where the climate models are. And I can talk more about that, if you're interested. Secondly, you see that certain models, like this is CNRM, actually showed a delayed pattern response, which isn't evident when you keep global mean. What it suggests is this particular model, as an example, has the right global mean, but when you remove that, its regional patterns of warming are delayed compared to others. So one could imagine using these tools to try to assess differences across climate models. And finally, you may say, this is still temperature. Temperature is sort of boring. Okay, how about precipitation? Precipitation is a lot more complicated and a lot noisier than temperature. And when we look at precipitation, the neural network, so precipitation is very noisy with large disagreement across climate models. And even still, the neural network can identify the year from maps of precipitation in models, as you can see, but also in observations in white, although they're nowhere near as good. You see how the slope is much shallower. So those predictions aren't anywhere near as good as those for temperature. But the point is, it's not all noise. So this neural network is finding these reliable patterns in various variables. Okay, so I told you I was going to set up the problem, and we were going to make a prediction that was boring. And ultimately, you probably agree that predicting the year is pretty boring because we all know what year it is, especially this year, right? We don't need a neural network to tell us it's 2020. But the question is, wouldn't it be cool to know how it figured out what year it was? What patterns does it use? So to do that, we're going to turn to neural network visualization. And you can think of it as taking a black backpack and putting it through an X-ray scanner at an airport. You get an inside view. It's not a perfect view, but it's a view nonetheless of what's going on inside of the network. So let me show you one of our favorite visualization tools known as layer-wise relevance propagation. This is not the perfect method, but it's one of our favorites. And this is my graduate student, Ben Toms, wrote a paper on using LRP for geoscience applications, if you're interested. It just got accepted last week. So we take some input, say of a cat, and the neural network outputs the probability that there's a cat in the image. And what this method does is it takes that probability and it propagates it back through the network to create a heat map of where the network thought, of the regions the network thought were most relevant or important for making its prediction. So put another way, you input this picture of a cat, and this method, LRP, gives you a heat map of where the network looked to determine it was a cat. So the regions that are important. Let me show you quickly, this is a fun little example of how this works. So this is from the paper of the computer scientists who developed this method. Where did the neural network look to determine there was a horse? So everybody look, you know, we all agree, I think, how we knew there was a horse. So this is the output of these heat maps where the red indicates where the network looked. And in some cases, you can sort of see if you squint that they generally line up with where the horse is. How about here? Where did the network look to determine if there was a horse? This is where the network looked. Everybody see where is it looking at the horses? No, it's looking at the copyright symbol, because the network has learned that if it sees this particular German copyright symbol, there's probably a horse in the image. This, as scientists, is absolutely not what we want to happen with our science. But this visualization tool can help us determine whether the network is doing what we want it to do, but also to learn new science. So let's apply it to our problem. If you remember, this is our network setup, and we want to know which regions are relevant for correctly predicting a specific year. So we can then back propagate using layer-wise relevance propagation, our predicted year, and output a map that looks like this. And this is the relevant region of temperature to predict the year 2015. So these are the regions the network thought were most important in knowing it was 2015. Now, the cool thing is I can do this for more than just 2015. I can do this for lots of different years and start to compare them. So here, we've done this for 1995 through 2095. And as you can see, these regions change through time, the regions that the network thought were most important. And in the upper right-hand corner, that's the forced response. That's a response of temperature to climate change. There's no question about that. That is the response. However, the network is helping us find the most reliable regions to focus on in trying to look for this. Now, why aren't all regions reliable? Well, the reliable indicators of a changing climate are a combination of where the climate change amplitude is large, that is where the upper right-hand panel has big values, but also where internal variability, or where the noise is smaller. And finally, where the models agree. Because if the models disagree, the network is going to learn to not focus on that region because it just doesn't know what's happening. Now, remember I mentioned the Arctic, or Arctic amplification. You might think, oh, that Arctic signal's huge. The neural network should just look at the Arctic to figure out what year it is. But if you look, there isn't much of a signal at high latitudes. And the reason is, while the climate change amplitude is large, internal variability of the Arctic system is huge. That is, your signal is big, but your noise is also very big. And also, climate models disagree on what's going to happen in the Arctic because they, for example, melt ice at different rates. So the neural network has learned that the Arctic is not a great place to look to get a reliable indicator of the year. Another example for fun is if you look over Southeast Asia, we can make a time series of how important that location is to the neural network's prediction, and we see that it peaks around the 2000s, and we're guessing that this is the network picking up on an aerosol signal over this region. Okay, I'm almost out of time here, so I just have a few more slides. The neat thing is this layer-wise relevance propagation allows us to use it for the observations as well. So for example, on the left-hand side is the actual temperature anomalies from 1997. This is the actual map. We can push that map through the neural network, and guess what the network predicts? It predicts it's 1997, which is amazing, okay? But now we can ask, where did the neural network look to know it was 1997? And again, it's where did it look in the observations? And we get the plot on the right. And you'll notice some regions pop out. And for example, the Southern Ocean is a very important region. And you'll also notice that the regions of the largest temperature anomalies, for example, this was a very strong El Nino that year, are not necessarily the regions that are most important for the network's prediction, because whether it's El Nino or not does not help the neural network know what year it is. And finally, and this gets a little technical, but I do want to add this for those interested, we can use other network visualization techniques to play a few other games. For example, when we removed the global mean from the map, it's a much harder problem for the neural network. And here, for example, is the observed map for 1985 of temperature anomalies. So this is, again, what actually happened. The neural network read this in and predicted it was 2016, so nearly 30 years off, okay? So we can ask the question, how should we modify the observed map to get a perfect prediction? And there's a tool called backward optimization that allows us to answer this question. And it tells us that this bottom plot is how we should change the 1985 plot to make the network guess the perfect year. That is, the models are too cold over land compared to the oceans, and that's why the network is getting confused about the real world. So this starts to help us understand where the climate models are wrong or biased, because the neural network could only learn those biased, the information from those models. Okay, so in wrapping up here, so looking ahead for machine learning for the geosciences, there are a lot of challenges for using these tools for science, and specifically earth science. One, in earth science, we have a lot of spatial and temporal structure to our data. High dimensionality, a lack of concise object definitions. This one's really interesting. For example, I don't think anybody's going to disagree where a dog stops and the air begins. We can all generally agree on that. Or what a dog is in the first place. We have even DNA to tell us whether it's a dog or not. But yet, as earth scientists, and I'm sure for all of you, you can think of examples of phenomena that this community is still arguing about how to define. And that's an example here of we don't really know what it is either yet. We don't have DNA. Positive ground truth, that is, we don't necessarily have millions of samples of images of cats that are labeled cat. Someone has to do that. We have a lot of rare classes. Extreme events, for example, extreme weather events are incredibly important, but by definition, they don't happen very often because they're extreme. How can we train a network to learn these features when we don't have that many in the observations? But finally, Unlike for many mainstream applications in the commercial sector, geoscience phenomena are governed by physical laws, right? Physics, where we all do some physics. We don't want to throw out F equals MA just because machine learning came along. We have done hundreds of years of work on these topics. We should use that. And so that brings me to this concept of physics-guided machine learning, which right now is the very hot topic in the last, I'd say, year and a half. And there are multiple ways to do this. The first is one that I'd showed you already, which is using visualization methods to see what the network is learning and help you modify the network to conform to physics that you as a scientist know exist. And the second is to actually incorporate physics into the training of the model itself. For example, there are some examples, recent examples showing penalizing the neural network when it breaks a physical law that you know is true. And it teaches the network to try and not break that physical law when it's learning its predictions. And so this is a region that's incredibly exciting in my view. Okay, so final slide here. My big 3 takeaways. I never expect anybody to remember the details of my talks, but if you were to take anything away, it's hopefully one of these. The first is that artificial neural networks can identify forced climate patterns. And I didn't show this, but we have shown that they can identify these forced patterns as early as the 1960s. Secondly, neural networks are no longer black boxes. They're not perfect either. You can't see all the way inside, but tools exist to help visualize their decisions. And in my mind, this is an absolute game changer for us as scientists. We can suddenly use these tools for more than just prediction. We can start asking why and how, which I would argue is our entire careers. And finally, as I just said, neural networks can be used for more than just prediction. The science can be what the networks learns. In my case, the science is the maps, the regional indicators, not the fact that it can predict the year, which we can all do as well. So the science can be what the network learns rather than the prediction. And why I love this stuff is it means we get to be creative and try and brainstorm crazy ways to use these networks to answer the science questions that we're most interested in. So hopefully that gets you excited too, because I'm having lots of fun watching the world use these tools in new and innovative ways. So thank you. That's it.
Thank you, Dr. Barnes. That was a very interesting talk. So now moving on to question and answer session, you can type your questions here. So in the Q&A box, or you can use the raise hand option. So the very first question is the activation function random in nature? Is it designed to fit data?
So the activation function is a choice that you as the creator of the network actually do have to choose. So there are there are many different nonlinear functions out there. They have to abide by certain rules, but otherwise you could make up your own. But there are a few common ones. For example, hyperbolic tangent is one that is used. So it looks sort of like that. Something called ReLU, which is 0 for negatives and then x equals y for positive values. So there are just a set that people tend to use. Is that your solution isn't too sensitive to this choice, but if you have the computational power, in my case I did, I tested a lot of them to see how they did and if they generally gave me the same answer or not. So it's not random, it is a choice that you make.
Okay, thank you. So the second question is, I have 2 questions. I think this is from Moha, about the model spread in early years and lack of physical mechanisms. Oh yeah, we can. Valentina, can you unmute Moha?
Yeah, give me 1 second. I'm looking. Oh, I think he can talk now.
Yeah, do you hear me?
Yep.
Yeah, thank you, Dr. Barnes, for the talk. It's really interesting. And yeah, I have 2 questions because, I mean, if you go back on your plot regarding the prediction of the temperatures in your neural network model, you see the spread in the early years, if you go back there.
Yep, hold on, go ahead.
if about the spread, I mean, the spread is you're starting a bit 1920s, where the models need a kind of period where you have a spin up of the in the model simulation, and they are also less constrained. Therefore, I would say I'm not surprised to see how spread they are, because more you go in the later years, more you get more reliable observations that are constraining the models, and then you get a better temperature, surface temperatures, right?
So first of all, these models actually did not start in 1920. Their spin-up periods were thousands of years before this. So there's no spin-up issue here whatsoever. In terms of constraining, in the big picture, no. These climate models are called free running, so they should not be constrained in any way. However, you're on to something. And that is, if you're going to design a climate model, you're probably going to compare its surface temperature to the real world and make sure it's not crazy.
Yes.
So, these are not constrained per se, but the humans that created these climate models certainly looked at the observed surface temperature and tried to make their climate model look okay. So in that sense, I agree, it's not as surprising that the observations fit so well. However, it is perhaps surprising when we take away the global mean, or when we start looking at other variables, because climate model developers aren't looking at all of those at the same time.
Yes, I think the other point, which is quite interesting, is that when you remove the mean, that the prediction get a little bit shifted compared to
and that means what the network has learned, it finds a disconnect between the models and the observations.
Yes, it means then in the climate models, we need to fix better maybe the interannual variability, or at least the natural mode of climate variability, like the aerosol forcings, like when you have a volcano.
The forced part,
Yes, like or the El Nino's representation. If you have a coupled model with the ocean, mainly that the models lack also of getting the sea surface temperatures right, for example.
Possibly, except remember, the hope is that the neural network has learned to ignore ENSO, because it's not a form of forcing. But yes, all of these things, the noise in the climate models as well as the force response, are all coming into play. So it's a bit of a mess.
Yes. My second question was about the physics, because actually, if you go back where you're comparing the El Ninos, the 1970, there was a strong El Nino that is not really captured, on the prediction. Would you mean that is it that to the fact that the El Ninos is creating a perturbation on the temperatures, that the prediction model is not is only based on the mean, is not seeing the El Nino's effect?
No. So we don't want it to use El Nino. So the neural network, El Nino, whether it's El Nino or an El Nino or not, is not useful information to know what year it is. So what this plot is trying to show is that the network has correctly ignored this region of the tropics because it will confuse it. So it's in essence, this is not an error, this is the opposite. This is actually saying the real world had an El Nino, but we know that's not a climate change signal. That's just internal variability. And the network on the right has learned to not focus its attention there, but rather to focus on the Southern Ocean, because that is a better indicator of climate change.
But do you think, because with the climate change, there are climate models are predicting that there will be a shift on the permanent state of the El Ninos, like you will be toward more El Ninos condition like, therefore it will also impact the circulation, the tropospheric circulation, as well as the stratospheric circulation.
Yes, and that's super fun. And actually, we're designing networks to help us explore changes in internal variability due to CO2. However, I don't think that's what this network's picking up. This network is doing something much easier. I think it's looking at, hey, it's hot here. It doesn't need that nuance yet. But actually, I have a postdoc right now who is starting to explore that very question. How can we use this setup to look for changes in internal modes of variability? That's not what's shown here.
Because I'm also doing more looking at the impact of the natural variabilities in the circulation changes, more stratospheric circulation changes, and how that impacts like the trace gas, like ozone, water vapor, focusing on Kibeo, Enzo, volcanic aerosols, and so on.
Cool.
What I'm wondering, like, if you would use these kind of models, then especially in the upper regions, in the polar regions, where, for example, you see that when you have El Nino year, it will impact, for example, the strength of the polar vortex due to the wave propagating inside the stratosphere, and then this will feed back the surface temperatures as well, and how. I mean, changing the state of the polar vortex will change also the ozone inside the polar vortex, and that also has a feedback on the surface temperature. Do you have an idea how to take into account, for example, the chemical processes and so on in that term, that you also would take into account this kind of feedback of how the polar vortex will change, and that will feed back to the surface, for example?
The network setup I'm using right now, in terms of all the mechanisms, those have to be captured within the climate models upon which it is learning from.
Okay, yeah. Okay.
So the network itself is not learning that.
Yes, okay.
But the models are,
okay,
if they can do it.
But is there a possible, because if you want to apply it with something much more complex, like let's forget how we could improve, for example, climate model using this neural network.
You can use it for many things, yeah. So you can use it. You can be creative and come up with a way to use that to address the mechanisms you're interested in.
Okay.
But not the setup I have here.
Okay.
Thank you. Yep. So we have more questions
Thanks.
from other attendees as well.
That's all. Yeah. Thank you.
Okay, so the next one is thanks from Marisol. Thanks for the talk. It was fun, pedagogical, and interesting. My question is, what's the optimal length of training data? Longer, similar than for linear regression?
Great question. First of all, I want to say in our second paper here, we've done this problem using linear regression as well, so you can compare to linear regression and get a feeling. The answer is absolutely no question. You always need more data than you would for linear regression because you need to learn nonlinearities. So no doubt you need more data. Unfortunately, there is no answer for a quote, how much data do you need? Just like there's no answer for how much data do you need for linear regression. It matters what your signal is and what your noise is. Same here. I think a good rule of thumb is you need a lot of data. Otherwise, you shouldn't be fitting anything nonlinear in the first place. Now, what is a lot of data, right? It all depends, again, on your problem and on your signal to noise. In my case, a lot of data is actually not that much compared to how much data was needed, say, to identify cats and dogs and horses and images. So sadly, there's no real answer. But my one rule of thumb I tell everybody is, if linear regression does a good job, don't go to nonlinear. There's no point. And secondly, if you can't get linear regression to work, or you don't have enough data for linear regression, then I promise you nonlinear regression is going to do even worse. So that's my sort of rule of thumb there, sadly.
Okay, so a lot of people are asking this question. Could you please suggest some introductory material, like book or review articles to read and learn AI?
Oof. So there's no review article out there that is going to teach you these methods. It's like the world of machine learning is like, can you teach me all of math and statistics in a review article? And you would say, of course not. Now, with that said, if you bite off small chunks, you may be able to do something. As I said, my graduate student, Ben Toms, this paper here is, it says, yeah, in press, there we go. This paper just became available. He has it on archive, but it just got accepted last week in James. This is our attempt to take this method for visualization and put it into the language of geoscientists. Because I will be honest, the language of computer science often confuses me. They use words I don't understand. They use math symbols I've never seen in my life. So we are trying to do this and write this for our community. And there are a few great papers out there. Amy McGovern has a paper like this. I should put up a list. And then there's another paper, there are a few other papers out there from our field trying to put this into our language. But the answer is there aren't very many yet. My biggest suggestion, however, is to get a book, or what I do is there are so many good, amazing blog posts out there about Machine Learning 101 that I spend most of my time reading those, and that gets me up and going. I think the most important thing, though, is that you do spend the time and you don't treat them like black boxes, because even things like linear regression, right? You can still do them wrong if you don't understand your data or the method. Same here. Make sure you understand the method and your data before you apply them. But yeah, that's I think we can do it. I think we're trained to do it, but it's going to be some slow steps, and it's not going to be one paper that gives you all the answers.
Okay, so the next one is from Rachel. Thanks for the nice talk. Have you looked at the visualization patterns in the future projections? I'm wondering if similar model bias pattern you showed would change in the future.
So I've looked at these patterns. So these are all based on the climate models through 2095. So this is showing the visualization patterns that are important for the future, and they are different than those of the past. And this is again reflecting changes in signal, noise, and model agreement. So maybe you mean that. If you are referring to these types of patterns, so model biases, I have looked, so this is for 1985. I have done this again for, say, 2005, and the patterns are generally the same, suggesting at least over the last few decades, the climate model biases that are most important are still the most important, which actually makes me feel good, because over only a few decades, we don't expect the model biases to necessarily change drastically. So hopefully that sort of answers your question.
Okay, the next one is, do we need to consider the data quality? How much important is data quality?
Machine learning tools will only learn what you give it. If you give it bad data, it will learn that bad data really, really well. So in terms of data quality, if you don't trust your data, then you're going to have issues, because that neural network or that machine learning algorithm is going to learn the data you gave it. With that said, there are really cool and innovative methods these days using machine learning tools to help clean the data, help improve the data when it isn't good, fill in holes where you have missing data. There are a lot of cool methods out there. There's a paper that just came out in the last few weeks trying to make fill in the gaps of surface temperature maps all the way back to the 1800s using a convolutional neural network, and it's pretty amazing. So in that sense, data quality is very important. However, these tools can also be used to help with that if you do have good data somewhere else too.
The next one is, do you think AI is still so expensive for global cloud and ocean eddy resolving models?
Yes, so it's still so expensive. I mean, doing anything with clouds and eddy resolving is really expensive. But the hope is that these tools, if we can make better parameterizations of, say, eddies or convection, that they will speed things up considerably. But I think the question then is, right now, a big question is, these parameterizations are doing a very good job over, say, the historical period, but they don't do a good job at predicting future physics. And so how can we deal with that? So I think the whole point of machine learning techniques for climate model development is hopefully to speed them up. But I don't think we're there yet.
Okay. Very nice talk, thank you. Didn't you try to use a small convolution neural network instead of a feed-forward neural network?
So we've talked about using a convolutional neural network. We're going to try it. I'm not convinced it's going to do all that much better, and that's because if you're familiar, it sounds like you're familiar with convolutional neural networks. I'm not sure there are really small-scale features that it should be looking for to identify the patterns, because the patterns are really based on their location on the globe, rather than trying to find, say, a cat ear anywhere on the globe. We want a cat ear specifically located over the tip of Greenland, because that has something to do with the oceanic circulation there. So I'm not convinced it will do better. CNNs are really useful when you have overfitting issues. And in our case, the way we get around that is we use a form of regularization. I just threw a lot of vocabulary words at you. But just to say, we have not tried it, but I'm not convinced it's going to do any better. But we will. That's on the docket.
What is the state of machine learning in understanding the dynamics of the future climate system apart from identification of patterns in existing data?
I don't think, what is the state of the dynamics of the future? I think relatively non-existent. I think there's so many fun things we could do. There are a few papers out there, but not very many. And one of the big questions is, how do we do this to understand the dynamics? How do we set these tools up to be more than just prediction? How do we set them up to actually answer science questions? And I think as scientists, this is where you guys can be the ones to do that. For example, going back to cloud parameterizations, we have cloud parameterizations that we've used machine learning to figure out what those should be. But then when we try and have those parameterizations run in a future climate simulation with CO2, they fail miserably because they haven't really grabbed the physics right yet. They haven't really identified the right physics. So I think there's a lot to be done here. I'm not familiar with much in the way of actual dynamics, which is one of the reasons I want to be in this field, because this is a lot of fun to do both dynamics and machine learning at the same time.
Is there a way, okay, I'll ask the question, yeah. Is there a way of assessing what signals, for example, low frequency variability, your results are failing to capture due to insufficient input data of those processes?
Is there a way of assessing what signals your results are failing to capture? I suppose one method could be to go and look at when it was wrong and figure out what's consistent across many wrong answers to try and identify certain climate states that really confuse the network. Going back to sort of good old fashioned averaging, you know, hey, this one was wrong and this one was wrong. Let's average those two together and see if there was something the same about both. So that might be a way to approach it.
When working on a machine learning project, how much time do you spend on designing the project, preparing the data, running the model, and post-processing?
I would answer the same amount of time for all of those as I spend on a non-machine learning project. So in my view, there's nothing special at all about machine. I truly do view machine learning as just another tool. I have a lot of tools. I do averaging, I fit lines, I do cross-spectral analysis, and this is just another tool to help me do my job. So in that sense, no more time than anything else. Perhaps if I go to code up a convolutional neural network for the first time, I will spend more time writing that code because I haven't done it before, but that's same with any other method. In terms of preparing the data, like with any analysis method, I think preparing the data is about 90% of all of the work. You have to get the data into a way that makes sense as a scientist. For example, in my field, if you don't prepare data, you almost always will extract the seasonal cycle. And you will be amazed by how, the seasonal cycle is everywhere. So one of the big tricks is always thinking about how to get rid of that. And so, my answer isn't very useful, but I don't see this as any different than any other project I do.
So we're almost, time is almost over. So we'll just take the last question. My question is about beyond temperature and precipitation. What do you think about possible complications or uncertainties to face if you apply these methods you present to other variables like surface wind or humidity? And what about the case of using regional models?
So this is what we're actually doing right now, is temperature and precipitation were sort of our test cases to make sure it worked. And now we're going and starting to look more at extremes. What are some, you said, what are the possible complications? Fewer samples. If they're extreme events, they happen less often. And if they happen less often, we have fewer samples, which means it's harder to learn, which means we need more data. So those are the complications. I still think it's gonna work, but that's definitely the issue. So surface wind is noisier, so we need that much more data to extract the signal. But again, we are looking at circulation and dynamics to try to look at internal variability changes with anthropogenic forcing. And you asked about regional models. We have played around with, you know, I've been showing you maps of the entire globe. But what happens if you only look over South America? What patterns does it pick up then? As you can imagine, the smaller your regional scale, the harder and harder it is to extract a signal from all of that noise. But there may be some locations that still are very reliable indicators. And so one of my graduate students, Jamin Rader, is currently thinking about how do we use regional scale information to be able to say something more about, say, North America or Northern Africa than just the globe as a whole. And in addition, not just regional, but also my examples were for annual means. Well, seasonality, we know in terms of, say, the wet season and the dry season hold different signals. What if we bring that information in? Can we do better than we are now? So that hopefully helps you out. And I do, just quickly, I know we're supposed to end. I've seen multiple random forest questions. Random forests are another great technique and tool. They can be just as good as neural networks. They can fail when neural networks succeed. They can be better. It all depends on the type of problem, and there are some good rules of thumb for when to use one versus the other. I have not used random forest for this application, and I have various reasons that you can always email me. Great. Priyanka, I 1 minute, 2 minutes over here, but
no worries.
Hopefully that's okay.
Yeah, thank you for your time. So
great.